Welcome back, young men and young women, and the young teachers, my colleagues. Today, after finishing off a couple of chapters on magnetism and the properties associated with magnets, after finding what are the various kind of materials, etc., etc. Okay, today I take up the beautiful, the ever beautiful electromagnetic induction. Electromagnetic induction, which we learned during the course. Oersted and Ampere and others were doing their experiments and they gave beautiful results, okay, which we have enjoyed in the past 10 lectures or so. So there came the year 1830, and then we are told about one Mr. Micheal Faraday, which I say Faraday the Great. And there was Joseph Henry. This gentleman was a professor of experimental physics at the renowned University of Princeton in USA. Now it has been renowned, it is renowned, and hopefully it is renowned. This is one of the Ivy League universities, okay, top universities. So Joseph Henry in USA, a professor particularly of experimental physics, and a young Micheal Faraday, I call him Micheal Faraday the Great, a young apprentice to the scientist at the time, Davy. You must have heard about Davy's lab. Old man Donald, and he needed a apprentice to work with him, bring this, bring that, put it here, put that there, put it in the shelf, bring it from the shelf, type of an apprentice. Similar to what we find our chotus in various dhabas, chai outlets or otherwise, who are young, very smart boys, energetic, and they are put to work by the owners. Okay. So Micheal Faraday was not a man of letters. Micheal Faraday had a place in his house which was not being used. It was hardly about 8 to 10 square feet. And this son of a blacksmith, eighth son of a blacksmith, it is said, this young boy, while his siblings were working, he started working to substantiate the income of the family. We were lucky that Micheal Faraday got a chance to work with the aging Davies. Micheal Faraday, he used to experiment as he wished, used to study also. when time will permit. Books from here and there and there and here. And it is said that he became friendly with the bookseller. Okay. Now they found, they conducted, and it's not said who conducted what, but both are given the credit, Professor Joseph Henry and the young Micheal Faraday. 3 experiments come up, and in the first experiment that I have marked here, what we have, I don't have a challa, okay, so this is a loop, and in this loop, let us confine to this loop, and let us have the magnet as it was. Now, by the way, or by design, or whatever, they had this wire, single winding and N turns, doesn't matter, and that was connected to a galvanometer, okay, a meter, which could indicate whether there is a current or not. Now, by providence or otherwise, by our good luck, Micheal Faraday conducted an experiment. He had the magnet, and this side North Pole, this side South Pole. We have learned that this will have a magnetic field on the axis of the magnet. I have solved that. You know as to what will be the value at a distance x, etc., etc. And we know that as the distance is increased, the field value is reduced. As it is decreased, if from here to here, then the field value will increase. Now, when the north pole of this magnet, or the magnet itself, it is brought, it is moved towards the loop. Oh my, there was no connection between this and this, and he found that the galvanometer gave a deflection. They found that the galvanometer gave a deflection. He stopped it at a certain position and found that the deflection subsides, becomes equal to 0. Then he withdrew this, took it away from the loop, and this time, look here, what happened was that the deflection in the galvanometer, that was reversed. Wow. So then he changed the north to south, and then again when you bring it closer, then the current will flow. Here the deflection will be there, but opposite to the direction when the north pole was approaching. If being withdrawn, then opposite to the direction, okay, that direction, that means in line with the direction when the north pole was approaching. When it was stopped anywhere, the deflection became equal to 0. Micheal Faraday, the unlettered man. Of course, he was being trained by very important physicist, engineer, whatever you want to say, a Jnani like Davies. And then he found, now what he did, what they did. Let's give the credit to Henry also. What was done was, the magnet was put as it is, and instead of the magnet, the loop was now brought closer, moved towards the magnet. There is a deflection. It was taken away, there was a deflection. It was stopped, the deflection did not take place. So, reverse the poles, south pole here, north pole here, and then again the same thing was conducted, and they found that yes, why? There is a relative motion between the magnet and the loop. Remember that, a relative motion. If both were taken on a tray, nothing will happen, because there is no relative motion. So he would jot down everything, whatever is happening, must have discussed with the old man Donald Davis. I don't know. There is no record of that. But the experiment was conducted. And this was for the first time. It was revealing that because of a changing magnetic field, the magnetic field was changing. Okay, like all the time. Okay, the magnetic field was changing. So if there is a changing magnetic field, it gives rise to a deflection in the galvanometer. Deflection means there is a current which is flowing. And what does it require for the flow of a current? There should be an EMF, a source of EMF, which is not there. So that means that kind of an EMF is subjected over here somewhere, and the current flows. This, that, this. Okay, sir, it happened like this, and he would show it. Maybe not. Then the little boy and the learned professor here, they are conducting another set of experiments. And what they do is that they replace this magnet by a current carrying coil, which has a source of EMF. And you know that for a coil also, I calculated the magnetic field at the axis of the coil. So the away it is less, the closer it is more, etc., etc. And they found similar kind of results. When this is brought closer, maybe the current in one direction, which is when it is stopped for some time, no current. When it is taken away, then there is again current, but in a different direction. But what he did then, he changed this, and instead he put this is negative and this is positive, which reverse the direction. Right? Again the same thing. Bring it here, take it away, stop it. Okay, let it be there, but let us move this towards, away, etc. So very interesting results, similar kind of results. Okay, so they were happy. Now this experiment It is said the third experiment was exclusively done by Micheal Faraday. Joseph Henry had not done it. What he did was, it is as follows, that he made an arrangement. Maybe there are n turns, doesn't matter. I've just shown you the simplest possible diagram. There is a key, and this key is a tapping key. Okay. So he put this with galvanometer, and then another coil where this is positive, this is negative, etc. Okay. What he does is that he taps the key. When the key is tapped, then during the time that the current builds up over here, okay, current will be equal to E upon R, where R will be the total resistance of the setup. That builds up and becomes the steady current flowing through this coil. But the moment the key is tapped, then there is a deflection in the other coil. Okay. Then it stops. No current, no deflection. When the current is flowing through it, it has become steady, etc., etc. Then you break the circuit. The tapping is removed. The moment you remove it, there is again a flow of current momentarily for a short period of time by which the current over here drops down from a finite value to a zero value. Okay. And then this experiment of Mr. Micheal Faraday, the great person. Why I say that, I said in the last lecture also that we should give him a name. From this platform of Learn Physics Online, that one of the people who we can call a great is Micheal Faraday. There have been greats up and down, but I call Micheal Faraday as a great because he was a self-made person. He was a self-made scientist. Now this young boy, he started thinking as to what is happening, and he found that probably it is because of something which is changing. Okay. And then he called it, and he thought and thought and thought that there is something which is passing through this loop. Okay. It is going in and out of it. This is passing through it, which is being reduced or is being enhanced. And that is what he gave the name flux. And because that flux was due to the magnet, he gave the name magnetic flux. And then he argued that it is the change of flux. It is the change of flux. The flux is there and this flux is changing, either going up or down, increasing or decreasing. And that increase or decrease of the flux is responsible for the flow of the current in it. Anyway, now he was not, and I don't know if Joseph Henry's days the dot product and the cross product were there or not. If you are interested, you can check as to when the vector cross product and dot product, etc. was started. Okay, it doesn't matter to us, history doesn't matter. Now, what I have is a uniform magnetic field. Actually, it is a I've not done that. So it is a uniform magnetic field, and it is going through a surface. A surface which has a vector perpendicular to it. I've told you that surfaces are vector quantities, surface areas are vector quantities. Some people, some books, they write it phi b is equal to b dot a, where a is the area. Doesn't matter. Symbols don't matter at all. Okay, as long as we understand. So, through this, if this is a ds element, then d phi b will be equal to b dot ds, and the phi b will be equal to integral b dot ds carried over the entire surface, or a summation over the entire surface. So this phi b is equal to b dot ds. Okay. And so came this formula. E is equal to d phi b over dt. From here also the same formula came. E is equal to d phi b over dt. Rate of change of flux is responsible for a source of EMF, so that there is generation of current or induction of current or induced EMF, which is responsible for this creation of an EMF. Okay. So 3 experiments, one exclusively for Micheal Faraday, and 2 of them, in those days, 1830s, and the connect between the United States of America and the Great Britain was through ships sailing from one place to another place. It used to take several months before you could go there. And the story is, it's a very interesting story. I'll talk about that. Another great, Thomas Alva Edison, who made the bulb, who made thousands of things. Okay. The story is that when he was a kid, the school sent a letter to his mother, etc., etc. Okay. Where he was described as an idiot, moron, etc. And the mother said, no, the school says that you are such a genius that they don't have teachers to teach you. So I will teach you. Anyway. So I'm not going to, yes. What happened that he was the first to use the batteries and a DC generator in the city of New York in those times. I will come to that story some other time. It's very interesting story. I will tell you about that story. Okay. This is very, because there is a boy who travels from USA to get to become wiser. He visits Europe and he visits some place in Italy, and this Joseph Henry is responsible for the transformers. He gave the idea of transformers. We'll have occasion to talk about it. So he was a great man in his, but readily, just after 1830, when Micheal Faraday got fame and people of letters and people who knew Davies, they were very happy with the performance of the young Chotu at that time, and they made him readily the member of the Royal Society of Scientists, and he was invited to deliver his lecture, his talk. So the young Micheal Faraday was delivering his talk about it, and the then Prime Minister of England, he was getting bored. Then he stopped him. While he was in full flow, he was stopped by the learned Prime Minister at that time, but he was an arrogant man because he was from the aristocracy, and here was a boy from among the smiths, workers, okay, and he was getting full applause from all people who were sitting over there, wondering what he's doing. Then he asked him, "Well, very nice, Mr. Faraday. I have seen these things with very intently, checked what you have been doing. But tell me, what is the use of doing all these things?" And Micheal Faraday came out readily with the beautiful statement, which is a flag bearer for science, and he said, "Sir, respected Prime Minister, can you tell me what is the use of a newborn baby?" Sir, all of us were newborn once upon a time, and today most of the people are paying taxes to the state. So like that, maybe my newborn baby may give taxes one day to the state of United Kingdom. And there was nothing like that at that time, whether this discovery should have been patented, and there were no multinationals, this, that, this, no capitalists at that time. Anyway, so Micheal Faraday's discovery today is responsible for the creation of the electricity in the AC form, and connected with Joseph Henry's transformer, step up, step down, where we increase the voltage or decrease the voltage at the ends of the wires, and how we take the electricity from one place to another place, and how we save on that, etc. So that goes to the discovery and works of the learned professor. Look here, but I will say that the law of Micheal Faraday and Joseph Henry was confined to what I have put here. E is equal to d phi b or dt. 1830. It took 4 years after that, and of course Micheal Faraday was in Europe, was in UK, in England, in London. Okay. But the ferrying across the information, etc., that travelled in a matter of days from the mainland Europe to the island called United Kingdom, Wales, this, that. 1834, and this German scientist Lenz, he put a negative sign over here. Look here, compare the two of them. Micheal Faraday and Joseph Henry, they did this formula. Micheal Faraday was a novice, But Joseph Henry was a professor of experimental physics. It did not occur to him. But what Lenz did, he put a negative sign. And these negative signs are often very desirable, very interesting, and in this case, it showed that there is kind of an opposition. Okay. So what is there? What is there? Let's go back to experiment number 1. Let's go back to experiment number 1. And we are moving the North Pole towards the coil. And a current is flowing. A current flows because of this change which is occurring. So what should be the direction of the current in it? I've told you that if there is, then the direction can be anti-clockwise, direction can be clockwise, etc., which I'm leaving to you to find what will be. But, and that is created over here by the flow of current. So, by the flow of current, when the North Pole is coming, either it should be a North Pole or it should be a South Pole. Okay, this side of the coil towards the magnet. What should it be? Okay, there hasn't to be a confusion. There has to be either a North Pole or a South Pole. And the North Pole is approaching, and the magnetic field due to that is changing. The flux is changing. Current is flowing. Okay. Now what is the dharma of this? Come on. Oh, thank you very much. No. The dharma is that the dharma is that I will oppose you. No. So such a thing is created over here that it opposes. What is creating it? The creator is opposed by the created. In Arabic, the creator is the Khaliq, and the created is the created, maybe is the one who worships Abdul Khaliq. So Abdul Khaliq, he used to be an MLA in my city, opposes the Khaliq. The created opposes the creator. And this is what is the essence of Lenz's law. Okay. And suppose the North Pole is being withdrawn. At that time the current should be such that this side is the South Pole. Hey, don't go. First time, hey, stop. And this time, why are you going? Stay. Okay. Opposition. Opposition. Why? Because if I move this magnet towards this, we do so, there is a movement, and the magnet is going this way. The magnet has a mass. Okay. If opposed, I have to do some work to neutralize the opposition against an acceleration and therefore a force which is created there. And when I am taking it away, then this says, oh, don't go. Then again there is an opposition. What has to be done? What Work has to be done. Whether you move this or you move this, there is a mass involved and work has to be done. And that means the energy should be conserved. So the Lenz law, and incidentally, whenever we write this expression, we don't write it as Faraday-Lenz law. Earlier we used to do that. We don't write it as Henry-Lenz law. Okay? We call it, in the name of this thinking physicist, theoretical physicist at that, Lenz law. So whenever we have to write that E is equal to minus d phi d or dt, we always say this is the Lenz's law. Okay? It has not got the name Lenz law, Lenz's law. Okay? So Lenz law. Now, I will tell you something very interesting to top it up. I leave it. I put you in the ocean. Okay? And it is your job to understand all these things all by yourself, including this Lenz law. Now look here. You are, from where you are looking, suppose there is a coil. Okay? And in this coil, etc., there is a galvanometer, etc., etc. There are a number of turns. And the current which is passing through it, when we look at it, it is what wise? Anti-clockwise or clockwise? Clockwise. Okay? And then if we make, so the current is clockwise here. When I make it like this makes an S, which means towards us, on our side, there is a south pole. Okay. So, magnetic lines of field, if there is a south pole, they enter into a south pole. I told you this thing. Some people say that the magnetic lines of field flow from the north to south. That's not proper. Magnetic lines of field always enter into a south pole and exit north pole, like this case. This is anti-clockwise. And if I write it, okay, when I do that, I find the figure of N, which says, look here, boy, I am a north pole. Otherwise also, if I hold it in the direction of the current with my thumb and my fingers will come out of it, then the lines of field will be out of it, and therefore we can say that this side has to be the north pole. Because they exit from a north pole, they enter into a south pole. So I am going to stop here. Okay, I'll go to other things shortly, but I've spoken to you something, one of the most beautiful statements. I gave you a statement of Isaac Newton. Okay, and he said, when people were praising him too much, he said, look, I am like a child. I am at the shore of the ocean, picking up the pebbles. And if you think that I am great, then always know that I am standing on the shoulders of people like Galileo, okay, people like Aristotle, and people like the people from the past. So I am not great, they are great. They have put me on their shoulders, so I look great. So friends, I have enjoyed, like I used to enjoy when I used to teach in the classroom. Okay, I have enjoyed, and I think I am not incorrect in saying that you must also enjoy. Thank you very much. Thank you.